Now let's look at a real-world, classic example of a system-on-chip, the NVIDIA Tegra 2. We've talked about how SoCs became popular in mobile devices, and this chip was a major player in the early days of tablets, back around 2010. The table on the left gives us a great summary of its key features. The designer, of course, is NVIDIA, a company you probably know from the graphics cards in gaming PCs. The processor, the main brain of the chip, is an ARM Cortex-A9. Notice it says dual-core. What does that mean? It means there are two independent processing units, or CPUs, on this single chip. This allows the device to handle multiple tasks more efficiently, which was a huge step forward for tablets at the time, making them feel much more responsive. The frequency, or clock speed, is up to 1.2 GHz. You can think of this as the heartbeat of the processor. It dictates how many calculations it can perform per second. It's paired with 1 GB of a special type of memory called LPDDR2. The LP stands for low power, which is absolutely critical for a mobile device that runs on a battery. Now, since this is an NVIDIA chip, it's no surprise that it has a dedicated graphics processor. Here, it's the ULP GeForce. Again, ULP means ultra-low power. So, NVIDIA took their powerful GeForce technology from PCs and engineered a highly efficient version for mobile use. This is what enabled tablets to have smooth user interfaces and play games. The process is listed as 40 nanometers. This number refers to the size of the tiny transistors on the chip. To give you some perspective, a human hair is thousands of nanometers thick. A smaller process number means you can fit more transistors into the same space, making the chip more powerful and more energy efficient. And look at the physical package size, just 12 by 12 millimeters. It's incredibly small for a complete computer system. In fact, it often used a package-on-package design, where the RAM chip was stacked right on top of the SoC to save even more space on the motherboard. The list of tablets it was used in, like the Motorola Sum and the Samsung Galaxy Tab 10.1, really grounds this in reality. These were real products that were powered by this exact SoC. The most fascinating part is the image on the right. This isn't just a drawing. It's a photograph of the actual silicon die, with the different functional areas color-coded. This visually proves the system-on-chip concept. You can see the two green blocks labeled Cortex-A9 CPU. Those are the two processor cores we just talked about. But look at everything else on there. There's a big graphics processor block. There are also highly specialized units: a video encode processor, a video decode processor, an image signal processor for the camera, and an audio processor. Instead of making the main CPUs do all this work, the Tegra 2 had dedicated hardware for these common tasks, which is much more efficient. You can also see the cache memory and various I/O blocks for things like USB and HDMI. It's a whole collection of different computer components, all fabricated together on one tiny piece of silicon. This is what an SoC is all about. After seeing a great example of an NVIDIA SoC, let's look at another major player, Apple. Apple is a fantastic case study because they design their own custom SoCs for their products, which gives them incredible control over both the hardware and software. This table shows the evolution of Apple's A-series chips, the SoCs that have powered every iPhone and iPad. Let's walk through it to see some of the key trends we've been discussing. First, look at the columns for SoC and CPU. You can see the progression from the A4 chip up to the A8. What's really interesting here is the evolution of the CPU core. The A4 used an ARM Cortex, A8, and the A5 used a Cortex-A9. These are standard, off-the-shelf core designs licensed from ARM. But starting with the A6 chip, you see the CPU name changed to Swift, and later to Cyclone. These are Apple's own custom-designed CPUs. They are still compatible with the ARM instruction set, but Apple designed the microarchitecture themselves. Why would they do that? It allows them to fine-tune the processor's performance and power consumption specifically for their devices and their iOS operating system, giving them a significant competitive advantage. Next, let's look at this CPU ISA column. ISA stands for Instruction Set Architecture. You can think of it as the fundamental vocabulary and grammar that a processor understands. We see a progression from ARMv6 to ARMv7, and then a major jump with the A7 chip to ARMv8. This was a huge milestone. The A7, with its Cyclone core, was the first 64-bit processor to appear in a consumer smartphone. This shift to 64-bit architecture allowed for more complex software and better performance, especially with larger amounts of memory. Now look at the technology column. The measurement here is in nanometers, nm, and it refers to the size of the transistors on the chip. We see a clear trend from 90 nanometers all the way down to 20 nanometers. This is a perfect illustration of Moore's law in action. As the technology shrinks, you can either make the chip smaller or you can pack more transistors and therefore more features and performance into the same amount of space. This shrinking process also makes the chip more power efficient, which is absolutely critical for battery-powered devices like phones. This leads us to the die size column. You might expect the chip to get smaller as the technology shrinks, but that's not always the case. For instance, compare the A5 to the A5X. The A5X has a much larger die size, 162.94 square millimeters. This is because Apple didn't just shrink the A5, they added a much more powerful graphics processing unit, GPU, to the A5X to drive the new high-resolution Retina display on the third-generation iPad. So, they used the benefits of technology scaling to pack in more functionality. Finally, the table connects each SoC to a specific date and the devices it was used in, making it very clear how this technology evolution directly translated into the new iPhones and iPads released each year. The pictures at the bottom give you a sense of what these tiny, powerful silicon brains actually look like. They are truly marvels of engineering. Alright, so we've established the motivation for SoC design and have a good grasp of its advantages and limitations. The next logical question is, how is an SoC actually made? That's exactly what we're going to dive into next, as highlighted on our outline, the SoC design flow. This part of our discussion is crucial. Think of it as the blueprint or the recipe for creating a complex integrated circuit. It's not a single action, but a series of well-defined steps and processes that take an SoC from a mere concept to a tangible, working piece of silicon. We'll be exploring the entire life cycle from the initial specifications through the intricate design and verification stages, all the way to manufacturing and final testing. Understanding this flow will help you appreciate the complexity and collaboration involved. It's a journey that involves different specialists, from hardware engineers to software developers, and even different companies that might be responsible for specific parts of the process. So, let's get ready to break down this journey step by step. This diagram lays out the entire journey of creating a system on chip, which we call the SoC design flow. It shows how an idea becomes a physical chip inside a device like a smartphone. You can see it's a complex process involving different companies and parallel development paths for hardware and software. Let's start in the center, which is the heart of the design process, typically managed by what's called a fabless vendor. These are companies like Qualcomm or Apple that design chips but don't own the factories to make them. Their first step is defining the SoC design specifics. Here, they decide exactly what the chip needs to do. A critical part of this is HW/SW partitioning. This means deciding which functions will be implemented as dedicated hardware circuits and which will be run as software on a processor. It's a fundamental trade-off. Hardware is very fast and power efficient for a specific task, but it's inflexible. Software is flexible and can be updated, but it might be slower. Once the plan is set, development splits into two parallel streams. On the left, in blue, we have the hardware flow. The fabless company will often purchase HW cores from IP vendors. IP stands for intellectual property, and these cores are pre-designed, pre-verified building blocks, like an ARM processor core or a graphics unit. This saves a massive amount of time. These different blocks are then combined in the integrated hardware step. Before spending millions on manufacturing, they run a functional simulation to verify that the digital logic of the hardware design is correct. At the same time, on the right side in green, the software team gets to work. They also purchase SW drivers from IP vendors. A driver is a specific piece of software that allows the operating system to communicate with a piece of hardware. They combine these drivers and other necessary code in the integrated software stage and test it using software simulation. Now, how do we ensure the hardware and software, which are being developed separately, will actually work together? This is where the middle steps are crucial. A common practice is to build a prototype on platforms, e.g., FPGA. An FPGA, or Field Programmable Gate Array, is a special chip that can be configured to behave exactly like the final SoC design. This allows the team to test their software on real, behaving hardware without having to fabricate the actual chip yet. This leads to the most critical integration step, HW/SW co-verification. Here, engineers test the hardware and software working together on the prototype to find and fix bugs that only appear when the two interact. Once the co-verification is successful and the design is proven, it's ready for manufacturing. The finalized design is sent to a foundry, a company that specializes in chip fabrication like TSMC. They handle the physical optimization and fabrication, which is the highly complex process of turning the design into physical silicon wafers. After successful fabrication comes volume manufacture and ship. Finally, the journey ends with the device vendors, companies like Samsung or Sony. They take the finished SoC, mount it on a PCB, printed circuit board, add other components like the screen, memory, and battery, and assemble the final products that we buy and use. So, you can see it's a global ecosystem, moving from core design to SoC design, fabrication, and finally integration into the devices we rely on. This part of the diagram, highlighted in the red box, represents the very heart of the system-on-chip design process. It's the strategic starting point called SoC design specifics and HW/SW partitioning. First, let's talk about SoC design specifics. Before any design work begins, the team needs a crystal clear plan. What is this chip supposed to do? This stage is all about defining the requirements. For example, if we're designing a chip for a new digital camera, the specifics might include: it must process images from a 20-megapixel sensor. It has to record 4K video at 60 frames per second. It needs to connect via Wi-Fi, and its power consumption must be low enough to allow for 5 hours of continuous operation. All of these requirements, performance, features, power, and cost, are defined here. Once you know what the chip must do, the next critical step is deciding how it will do it. This is the HW/SW partitioning part. The term partitioning simply means to divide. Here, the architects decide which tasks will be implemented in dedicated hardware circuits and which will be handled by software running on a processor. This is a decision based on trade-offs. Implementing a function in hardware as a dedicated physical circuit on the chip makes it extremely fast and power efficient. But it's inflexible. Once it's etched into the silicon, it cannot be changed. Think of a hardware video decoder. It does one job, decoding video, and it does it very, very well. On the other hand, Implementing a function in software means writing code that runs on a general-purpose processor, like an ARM core. This is much more flexible. You can update the software later to fix bugs or even add new features. However, it's generally slower and consumes more power than a custom hardware solution for the same task. So, the design team has to make a strategic choice for every single function. For our camera example, they would almost certainly implement the 4K video encoding in hardware for speed and efficiency. But perhaps the camera's menu system would be done in software, allowing the manufacturer to release updates to improve the user interface later. As you can see from the arrows leading out of this box, this partitioning decision kicks off two parallel development paths. The hardware tasks go down the blue path on the left, and the software tasks go down the green path on the right. This single step dictates the entire structure of the project. Finally, notice on the right that this entire design phase is the responsibility of what we call fabless vendors. These are companies that design chips but don't own the factories or fabs to make them. They create the blueprint, and this hardware-software partitioning is one of their most fundamental and important decisions. All right, let's focus on this central step in our design flow. Prototype on platforms, e.g., FPGA. After we've figured out the high-level specifications of our system on chip and decided which parts will be hardware and which will be software, we need to test our ideas. But how do you test a chip that doesn't exist yet? Well, that's exactly what prototyping is for. Think of it like an architect building a detailed scale model of a skyscraper before the construction crew ever breaks ground. You want to see how it all fits together and find any problems before you commit to the incredibly expensive process of building the real thing. In the world of chip design, our scale model is often built using something called an FPGA. So, what is an FPGA? The letters stand for Field Programmable Gate Array. Let's break that down. Field programmable means we, the designers, can program or configure it in the field, meaning outside of the factory where it was made. We can change its function over and over again. Gate array refers to the fact that the chip is filled with a huge grid or array of generic logic blocks and interconnects. Imagine you have a massive box of Lego bricks, not pre-built into a car or a house, but just individual, fundamental blocks. An FPGA is like that box of Legos. We can use a special programming language to describe the hardware we designed, our processor, our memory controller, our custom peripherals, and a tool will translate that description into a configuration file. When we load this file onto the FPGA, it electrically wires those generic logic blocks together to perfectly mimic the behavior of our custom chip design. If we find a mistake, we don't have to throw anything away. We just fix our design description, regenerate the file, and reprogram the FPGA in a matter of minutes. Why is this step so crucial in the SoC design flow? Because it bridges the gap between simulation and reality. The steps before this, functional simulation and software simulation, are entirely virtual. They run on a computer and are very good for catching initial bugs, but they can be very slow, sometimes thousands of times slower than the real hardware. And they might not capture all the subtle, real-world timing issues. By building a prototype on an FPGA, we create a physical, working version of our SoC that runs at or very close to real-time speed. This is the first point where the hardware design and the software can truly meet and interact. The software team can run their actual drivers and even applications on this hardware prototype, not just a simulation. We can connect real devices to it, like a screen, a keyboard, or a network cable, and see if our whole system behaves as expected. This allows us to move on to the next critical stage, HW/SW co-verification, with much higher confidence because we are now testing the hardware and software working together in a real, physical system.